Alright, today we're going to be taking a look at powers, exponents, and square roots. The vocab we're going to be looking at for this lesson include power, base, exponent, square root, and perfect square. So in your notes you should get down that a power is an expression written with an exponent and a base. This should be a review. So for example, 3 to the second power is an example of a power. The base number is always the big one, and the little one is the exponent. Tells us how many times it's used as a factor, because remember this is always about multiplication. So this is the number that's used as a factor, and this is how many times it's used as a factor. Now we can use geometric models to represent exponents, but it's really difficult with numbers greater than 3. But we can still write them using repeated multiplication or a base and an exponent. So for example, 3 to the first power would just be 3, or 3 to the 1, and its value is 3. The biggest thing to remember is any power or any number written by itself is always automatically to the first power. It's just implied that it's there, even though we don't write it all the time. So 3 to the second power, or 3 squared, would be 3 times 3 because we use 3 as a factor twice. It's written this way with the power. It would be a value of 9. Most common mistake that we see is that people take the base times the exponent instead of the base times itself, the number of times the exponent says. So you can kind of look, cubed, 3 to the fourth power, and fifth power. I would take note that squared always means to the power of 2, and cubed always means to the third power. You probably have quite a bit of experience working with integers and with exponents by themselves, but probably not a ton with the two together. So one thing to be aware of is when we start looking at negative numbers that are squared. In this example, negative 5 squared, 5 is the base because the negative sign is not in parentheses. However, in the expression negative 2 in parentheses, negative 2 is the base because of the parentheses. So let's just look at the examples. We have negative 5 to the third. This means negative 5 times negative 5 times negative 5. When you have negative outside or no parentheses written, it actually implies a negative 1 times 5 times 5 times 5. So let's take the opportunity to evaluate some expressions. Negative 6 to the third power, you notice it's in parentheses. This is going to be negative 6 times negative 6 times negative 6, which is really the same thing as just 6 times 6 times 6. We just have that negative in there. So if we do that, we get an answer of 216. Since we have an odd number of negatives, it's going to be negative 216. So why don't you go ahead and pause the video and try examples B and C on your own. Here we have negative 10 squared. Remember, so that means negative 1 times 10 times 10. So I'm going to do my 10 times 10 is 100 times my negative, so my answer is negative 100. And then 2 ninths to the second power, or squared, is going to be 2 ninths times 2 ninths. Multiply straight across. An answer of 4 ninths. There's no negative, so that's our final answer. One thing when we're working with math is we want to be flexible with our thinking. So one part of working with exponents is also being able to work backwards with exponents. And when we do that, it is writing a number as a power of a given base. So here we have 64 base 8. So essentially we want to make that look like a number in an exponent with 64 as our answer. A couple ways you can do it. For example, on A, I know that 8 goes into 64 as 8 times 8. So then that would be 8 to the second power. If you didn't know that, another way we could do that, so for example, 81 with a base of negative 3, you could do it two ways. You could say, okay, well, I have 3, and then 3 times 3 is 9, times 3 is 27, and then 27 times 3 is 81. How many times did I multiply by 3? 4 times, so this would be 3 to the 4th, but we want a negative, so I'm going to put that in parentheses. Or we could take 81, divide it by 3, because opposite of multiplication is division. 3 goes into 8 twice, which is 6. And then we have 27. And then I would do 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. And I would look at how many times I was able to divide by 3. Same thing, it's 4 times, so we'd still get that negative 3 to the 4th power. So why don't you go ahead and pause the video and try 27 to a base of negative 3 on your own. Now hopefully this wasn't too challenging, especially since we just used a base 3 in the previous example. So 27 is actually just one less, so since it's going to be negative 3, we could say that it would be, basically we would take this one out of our previous work, so we would divide by 3 times, so it's negative 3 to the 3rd power. Another way we become flexible with our thinking is when we start applying the idea of square roots. A number that is multiplied by itself to form a product is called a squared root, and you should get that down in your notes so you understand what that is. The operations of squaring and finding a square root are inverse operations. We use something called the radical symbol, which you should also get down in your notes. It looks like a little check mark. Is used to represent square roots. Positive real numbers actually have 2 square roots. For example, if you're looking at the number 16, we can get 16 by taking 4 times 4, which equals 4 squared. So the square root of 16 is 4. But we can also get 16 by taking negative 4 times negative 4, which is negative 4 squared, giving us a negative square root, or a negative 4. So there's always 2 square roots to every number. We denote square roots 2 different ways. One way is when we have a non-negative square root, when it's just, you'll see just the square root sign. If they want the negative square root, you'll see a negative sign in front of it. Sometimes you'll even see an operation that looks like that, in which case they're looking for both the positive and the negative square root to a number. A perfect square is a number whose positive square root is a whole number, so you want to make sure you get that down. Some examples of perfect squares are shown in the table. So we have 0 squared, 1 squared, 2 squared, 3 squared, all the way up to 10 squared. I think that it's beneficial to memorize your perfect squares all the way up to 15 squared if you can, just because they help you with factoring later on this year. The reason that these are called perfect squares is if you think about if I create arrays with these numbers. So 0, there's no dots. 1 would just be 1 dot. 2 squared would be a 2 by 2. So it looks like a square. 3 squared would be 3 times 3. So once again a square. 4 squared. Because we're multiplying each one by the same number, we have 2 sides that are the same, so it ends up being a square shape when we multiply it out. Now, one thing to note too is what's the difference between the negative symbol in front and the negative symbol inside the square root sign? Well, here's the difference. The expression of the square root of negative 36 does not represent a real number because there is no real number that can be multiplied by itself to form a product of negative 36. And that goes back to our rules of multiplying integers. By definition, a square root has to be the same number times itself. So for example, 36 can be achieved by taking either 6 times 6 or negative 6 times negative 6. However, with a product of negative 36, you'd have to have positive 6 and negative 6 because you'd have to have one negative sign. So the two factors would not be the same value, so that's why there is no real number. So let's practice. We're going to find each square root. So here we have the square root of 16, so what times itself equals 16 would be 4. And it would just be positive 4 because there's no sign in front of our square root sign. With our next one, we have the square root of 9. Well, 3 times 3 is 9, so this is going to be 3. This one does have a sign in front of our square root sign, so they're looking for the negative square root, so it's negative 3. This next one looks a little different because you see a fraction underneath. The way that we work this is we actually apply the square root sign to the top and the square root sign to the bottom. So the square root of 25 would be 5, and the square root of 81 would be 9. Once again, looking for the positive square root. So you go ahead and pause the video and see if you could do 121 by yourself. When you're looking at this, what times itself equals 121 would be 11. You're looking for the positive square root. Final answer. So key takeaways for this lesson is just some of those definitions, and then also just remembering what the difference is for the different square roots and understanding what a perfect square is.